I'll be covering some basics of neural networks, and this is an outline of what I'll be covering. So I'll start with some history from where we began this the journey of neural networks, and that includes McCullough-Pitts and perceptrons, and then we'll go to deep nets, and then we'll talk about some of the supervised learning algorithms like gradient descent and backpropagation. And then we'll talk about some of the regularization techniques, specifically dropout in this case, and then I'll go and show you a very simple tutorial in TensorFlow on doing very simple classification using these networks. So just before we go into artificial neural networks, this is just a very oversimplified schematic of a neuron, and we all know, but just as a refresher, so our brain is made up of billions of neurons, around 80 billion neurons. And what we see here is just a very simple schematic of a neuron, where it has these dendrites, which are the locations it receives inputs. And this is the soma, which is the cell body. And so the neuron is receiving inputs from these dendrites, and those inputs accumulate in the soma. And so what happens is that these inputs drive up the voltage in the cell body. And once this voltage reaches a certain threshold, it sends out a spike through the axon. And so this is kind of an all or none operation, right? Either you send out a spike or you don't. You only send out a spike or an electrical signal when your voltage crosses a certain threshold. And so now once you have this spike, then these signals can be transmitted to other neurons using synapses at these axon terminals. And so this is just a schematic picture of what a synapse might look like. So once you have a spike come in to the axon terminal, it triggers the release of certain neurotransmitters. So these are schematically shown bags of neurotransmitters. And in the receiving neuron, so this is the dendrite of a receiving neuron, there are receptors. And so these neurotransmitters bind to these receptors, which allows flow of signals into the receiving neurons. So this is called a synapse, and this region is called a synaptic cleft. And so what we call weights in artificial neural networks is kind of trying to simulate this synapse at the junction of two neurons. And so let's look at the first ever neuron model. So the first ever neuron model was proposed in 1943 by McCullough, who was a neuroscientist, and Walter Pitts, who was a logician who worked in logic. And so this is the name of the paper that first published this neuron model. And you'll see in the paper that it's basically inspired by the human neuron model. And so the model looks like this. There are a bunch of inputs, which are summed up, and then there is an activation function. In the case of McCullough-Pitts, this activation function was just a threshold, right? So if the inputs sum up and the sum is greater than a particular threshold, then you get an output. You get a certain output, and if not, then you don't. So there are certain assumptions that went into this model. So unlike the current neuron models that we work with, these weights in this model were fixed. So there's no memory, there's no weight changes over time, and these weights are completely fixed. The inputs for binary is all or none. So the inputs are either 0 or 1. And there is a fixed threshold, which mimics an activation function. So if your summed inputs are greater than this particular threshold theta, then your neuron fires. Otherwise, the neuron doesn't fire. So this was a simple model. And so this is an illustration of this, right? So you have a set of inputs, and these are excitatory inputs shown in green and some inhibitory inputs shown in red. The weights are fixed beforehand, and you have these inputs which can be 0, 1, right? And so the idea is that there is a threshold that you set for the model. And if the sum of these inputs exceeds this threshold, then you have an output of 1. Otherwise, you have an output of 0. And another way of looking at it is if you assume that there are no inhibitory inputs, so all your yi's are 0, then summation of your weights times your inputs, if it's greater than your threshold, then you have an output of 1, otherwise you have an output of 0. So this was the initial idea. And this kind of a model can be used to construct different computations. So for instance, here I'm showing an AND function, right? So you can set the weights and set the threshold such that this network now computes an AND function. And you can see that in order for this network to compute an AND function, you need the threshold to be 2 if your weights are 1 each, right? And so now you can imagine that if these both of these were 1, then the sum would be 4 and it would be above threshold and you will have an output of 1. But if either of these was 0, then you would not be able to get past this threshold and you'll have an output of 0. Similarly, we can also see that we can pick the weights and the threshold to implement an OR function. So in this case, our threshold just needs to be 1. And similarly, we can construct a NOT function using a weight of -1 and the threshold of just 0. So this is basically a network where you're building the architecture of the network in order to implement a certain computation. And so this is an interesting function. So XOR, exclusive OR, is an interesting function. And it turns out that you cannot actually just use one layer to implement this exclusive OR function. So you actually need 2 separate layers. And you have to set thresholds for all of those layers in order to compute this exclusive OR function. And we'll also see this again when we talk about perceptron. So overall, what we see is that if we look at the strengths of this model, we see that it ended up using neuron-like elements. It was inspired by the biological neuron model. It can represent any Boolean function. And we can potentially have recurrent connections even in this simple model so that we can add time and recursion to increase the power of the network to enable it to represent more complicated functions. And what's interesting is that this also has a seminal linkage between brain and computing. So it turns out that when von Neumann architecture for computing devices or computer architectures was designed, it was actually inspired by these logic units. And we see logic gates even in our processors, which were kind of inspired by the logic units designed by Michalowicz. And so, so those are the strengths. Can anyone point out if they can think of any limitations of this model? What can this model not do? Or what can be made better in this model?
It can't learn weights.
Right. So that's one. So the weights are completely fixed in this model. And that's a big one too. So these are this is basically a list of limitations. So basically in this model, we are actually designing the architecture for a given problem. So if we wanted to implement an AND function, we designed the architecture. We picked the weights and we picked the thresholds in order to implement this particular function. There was no learning involved. So all the weights in the model are picked beforehand and are constant. And it only acts on binary inputs. So there's no continuous functions involved. And then the inputs can only be either zeros or ones. And if the inputs are on, meaning they're ones, then you can't really assign any relative importance to these inputs. And what we actually want is a network whose structure allows for the implementation of continuous functions rather than just receiving discrete inputs. And that's where perceptron came in. So before I get into perceptron, I want to talk about these concepts of linear separability. So here I'm just showing schematically what linear separation means. So if you have a bunch of points in a space, so for instance here in 2D space, then if you can separate them by a linear function, for instance, here it's just a line, then you can deem those points to be linearly separable. Similarly, in an n-dimensional space, in this case, 3-dimensional space, if you can find an n-2 dimensional plane, so in this case, it's a 2D plane that can separate these points, then these classes are said to be linearly separable. However, if you have these points which can't be separated, so in this case, for instance, in this example, you can't really draw a line that will separate these two classes, and you have to kind of draw this nonlinear function. And so in this case, you can see that these are not linearly separable. And similarly, this is another example. And so formally, we can define linear separability in this form. So if you have an n-dimensional feature space of p points, then p points are linearly separable into two classes if there exists a separating hyperplane, which is n-1 dimensional. And this is the equation of that particular hyperplane, right? And so basically, if given any point, let's say x vector, if your xi, once you substitute xi in the equation of this plane, if it's positive, then your vector lies in one class. And if it's negative, then you can say that your vector lied in a different class, right? So here, vector x is representing each point p. And so when I say hyperplane, it's just something analogous to a 2D plane, but in higher dimensions. So what's important is to remember that if you have an n-dimensional space and you are trying to separate your points in an n-dimensional space into two classes, then you need a plane or a hyperplane of n-1 dimensions. So this brings us to perceptron. So you can see that this is a model of a perceptron. And what this is showing is that, again, you have a set of inputs, you have a set of weights which are summed over, and then there is an activation function. And so what we see here is that, let's just go to the next slide. Okay, so what I want to point out here is that when you're summing up, this is very similar to what we saw in Mikolowitz. So you have summation w times x minus theta. And here what we've done is we've added this theta as one of the weights, right? So here w naught is basically minus theta. So you can formulate this problem instead of looking at a threshold separately, we can look at it as part of this model by adding just one to an input vector and using this weight to be negative of this threshold. And the reason we do this is because in this case, we'll have to train these weights. And not in this case, but eventually when we train these weights or when we compute these weights, we want to be able to compute theta also as a parameter of the network. So this allows us to club all the parameters of the network into one single weight vector. And another thing I want to point out is that in this case, in the perceptron, we use Sine Non-Linearity. So basically, if your summed input is positive, then you get an output of 1. And if it's negative, then you get an output of -1. And these can be seen as two different classes. So you can kind of see the perceptron as classifying your data set into two classes. Or everything that gives an output of 1 lies in one class, and everything that gives an output of less than 0 lies in another class. So all positive samples in class 1 and all positive samples corresponding to class -1. And yes, this is how we can write that formally. So this is our activation function, signum function. And basically, W transpose X is a vector notation of writing this particular summation. So this particular summation can be written in vector form by just saying W transpose X. And when we apply this activation function to this, if this whole result is positive, then we can say that our input vector lies in class 1. And if it is negative, then this particular feature vector lies in class 2. And so in this case, again, going back to the equation of the hyperplane, this W transpose X actually defines the plane, the separating plane that separates these two classes. And so you can see from this equation that actually the weight vector is a vector that's perpendicular to that plane that separates these two classes. And when we'll adjust these weights, we are actually adjusting this weight vector. So this brings us to the perceptron learning algorithm. So the question is, how do we train weights in this case, right? In McCulloch's model, we just chose the weights ourselves depending on what function we wanted to implement. But in this case, we would have to train the weights or compute the weights in some way. So because one major difference in this case is also that your inputs do not have to be binary. Your inputs in this model can be any real valued inputs, and your weights can also be real valued weights. So now we want to find a way to compute these weights given our inputs or the training data. So our inputs in this case would be a set of vectors X, right, which each correspond to a point in space that we want to classify. And so this is the perceptron learning algorithm. So what we do is we start with a random weight vector and we pick a feature vector X, which is basically one given input, right? A feature vector is just one given input, which is represented by vector X, K. So this is input K. And so this is one input in the training set. So we pick one input in the training set and we compute W transpose X, which is the summation of input times the weights. And we see whether the network actually classifies this input correctly by passing it through the activation function, right? And if we see that the network actually gives us the result that is expected, so let's say this feature vector is supposed to be in class 1, and we see that this signum W transpose X actually is positive, then we don't have to do anything and we just keep the weights as they are. However, if this network actually classifies the input incorrectly, then we have to update the weights. And the way we update the weights is given here. So if we know that our input, that our output was positive, but we actually wanted it to be negative, right? Because it has incorrectly classified this particular feature vector, then we can modify the weights by saying that our new weights will be our old weights minus some learning rate times our input vector. And beta is some learning rate, some positive learning rate, which is fixed throughout training. And similarly, if our output was actually negative and we wanted it to be positive, then we can say that our new weights will be our old weights plus some learning rate times our input vector. And once we've done this for one given input vector, then we pick the next input vector from the training set and repeat this entire process again. So is everything clear up to this point? Do people have any questions?
Just a small question. So in this example, is beta just like a constant or is it a vector? And is it a constant because it's like linearly separable? Would that change if we were trying to do something more complex?
Yes, so in this case, it's just a constant. And we actually just use, so original perceptron just used the same learning rate for all input vectors. And in this case, actually, one of the limitations of perceptron is that it can only classify data sets that are linearly separable. Although it doesn't have much, it has more to do with the architecture and the processing part of the architecture rather than the learning rate itself. But it's true that in this case, it can only separate linearly separable data sets. So if you have something like what we saw before, like a data set like this, then the perceptron wouldn't be the best architecture to classify this data set. Any other questions? Okay, so this brings us to just a summarization of this learning rule in terms of an error. So basically, given, if we assume that Zk is the current output of the network that we receive, and T of k is the desired output. So this is just saying what the network output is and what our desired classification output is. Then we can kind of define this error as the difference of these two, the current output minus the desired output. And this learning rule can be written in a more general form, where W new is just W old plus beta times this error times your input vector. So this error would be either plus or minus 1, depending on whether how incorrectly you classified your output. So this is just rewriting these two, but it's just combining these two equations into one form using this error function. So in general, schematically, you can look at it as, you have a network which is called a perceptron in this case, and we have some input, a set of input output examples. So we know which classes they belong to, and we know what input vectors they are. So we use these pairs of examples to kind of train the weights of the network. So this is a form of supervised learning where you're giving the inputs, you know what the output should be, and then you tune the network output to match what you want the output to be using the error function, right? And so that's what we are doing here. So some of the strengths of the perceptron are that it can be generalized to a multi-class perceptron. So so far we've seen only one output unit, right? But we can also have multiple output units here. And in that case, let's say we want to separate the data into k classes, then these act as k classifiers, and whatever outputs we get from these, we can kind of do an argmax. So for instance, if this is the highest one, this has the highest activation, then we assume that the data set actually lied in class 1. If this was the highest output, then the data point lied in class 2, and so on. So this can be generalized to, rather than just classifying the data into 2 classes, we can generalize it to classify data into multiple classes. It's an adaptive algorithm. So unlike the Michaelopaths, the weights are learned. And then the weights are also learned incrementally, right? So we can basically tune the weights based on each input vector and keep updating them as we get more input vectors. And so it can also be shown that this algorithm is guaranteed to converge. Like you can show and prove this mathematically, that if you train it on enough inputs over a reasonable amount of time, your weights will converge to give you the right classifications for a linearly separable data set. And so this is still used for, if you have a data set, it's still used to figure out whether that data set is linearly separable or not. So let's say you have a data set, it could be any data set which you collected experimentally. And if you want to see whether that data set is linearly separable or not, perceptron is one way of doing that. You could pass it through the perceptron and see whether it can be separated. So maybe I should ask this, like, what do people think are the limitations of perceptron? I mean, this is not a trivial question, but since I mentioned it a little bit.
We have lots of data sets that are not necessarily linearly separable.
Exactly, yes. So that's one of the main weaknesses or limitations of perceptron. It cannot handle non-linearly separable problems. For instance, exclusive OR. And we also saw this with Michaelopaths, right? So we can see that, if we saw in Michaelopaths that if we were implementing an AND function, we could find this line, which kind of separates these points from this point. And if we are implementing, this is an OR function. And if we are implementing an AND function, we can still find a linear separation. But if we were implementing something like an exclusive OR, which basically means that these 2 points should be in one class and these 2 points should be in a separate class, then it becomes very difficult.
We can't see your mouse in case you are using the mouse to point to things, or at least I can't. I don't know about the others.
It's too bad. All this time I thought that you were able to.
I mean, your words were quite clear, so it wasn't a critical problem. But now with the points.
It's so weird. Can you see it now? No.
No. Oh, yeah. I can.
Oh, here you can see it. Okay.
Right.
Okay, so basically what I was saying was that if we think about an OR function, then we can find this linear separation such that it separates these points from this point which lies in another class. And similarly, when we are implementing an AND function, we can find this linear separation. But if we were implementing an exclusive OR function, then what we need is we want these 2 points to be in the same class and these 2 points to be in the same class. And there's no clear way of finding linear separability in these two. So these are actually not linearly separable. And so it becomes very difficult to classify these kinds of data sets which are non-linearly separable using a perceptron. Some of the other things are that learning can be sensitive to the initialization of the weights. And also the order of data, right? So the order in which you bring in the input vectors starts to matter, and it might affect the convergence time of the perceptron. And it usually finds the first separating plane. This should be plane. So it usually finds the first separating plane between the two classes. And so it doesn't really, once it is found the first separating plane, it wouldn't fine tune that plane further. So in a nutshell, the linear models cannot actually model an exclusive OR function, right? These two classes being the same class and these two being in the same class is just almost, it's impossible to classify these using a linear model. And so this brings us to a multi-layer perceptron. So in a multi-layer perceptron, what we do is we add an intermediate hidden layer of processing. And we train these weights in these 2 layers using the backpropagation algorithm. And we will get to the backpropagation algorithm. But what I want to point out is that this actually adds some additional processing power to the network. And now we have some additional terms, which I'm just going to touch on, but Min-Young will talk about them later. So this is called an error function, which is basically defining how you compute the error between the output you get from the network and your expected output. So in this case, this is just a squared loss. So if T was the actual output and T is the actual label and Y is the output that you get from the network, then the error is just defined as the square difference between these two. And then we can also use different non-linearities instead of just using the Sine Non-Linearity. If we want to have real valued outputs, then we can use non-linearities like the ReLU or sigmoid. And that allows us to have even more computing power because it makes the network more powerful because now instead of having just binary outputs, you can have more continuous real valued outputs. And so that brings us to deep learning. So if we take this network and we add more hidden layers to it, that's essentially what a deep network is. And the training algorithm in both cases is again backpropagation. And so the question is, what is the advantage of depth, right? So we are adding depth because each layer in itself is a processing step. And having multiple processing steps allows us to implement complex functions, which would include complex nonlinear functions. And we can draw a metaphor between neural networks and computing circuits. So in a computer, we have very simple, if someone has studied digital logic, then you know that when in digital logic, we have these simple Boolean functions like AND or AND gate, OR gate, NOT gate, and so on. And if we combine them, we can actually come up with much more complex functions. Similarly, we can think of a deep net as a neural computer where a single layer helps us implement a very simple function. But then if we have a sequence of layers, it adds more complexity and allows us to implement even more complex functions. And so we should also look at how neural networks are commonly used for classification. So here, usually if we want to classify in multiple classes rather than in just 2 classes, for instance, here, this network is just showing 3 classes. Usually at the output, we have the number of nodes, which is equal to the number of classes we want to classify into. And our prediction, if we do not normalize a prediction, the predictions are basically some numbers, and it's difficult to see what they mean relative to each other. So usually at the last layer, we use this nonlinear function called a softmax. And what this does is it takes these numbers in the outputs and it converts them to a probability distribution, right? Because this function, it takes the exponential of this output and divides it by the sum of the exponentials from all these units, right? So basically it converts it into a probability distribution. So at the output, we get probabilities, which for instance, it might be, 90% confidence in this and 5% and 5% each in other 2 classes. And so then we take the maximum of them, right? So whichever is the highest probability, that means the model has higher confidence that your input vector falls in that particular class. And so that's how we then determine which class the model outputs. Okay, so next we go to backpropagation and how it works. So there are a few key concepts. So there's gradient descent, and then there's backpropagation. And on this slide, I've just very simply mentioned in words what these mean. So gradient descent is basically a technique for computing and adjusting weights over the period of training. And so the main idea is that the error from the network is dependent on the weights. Because if you look at this network, right, this network is composed of a bunch of weights. And we want to find the optimal weights. And we know that the error at the output nodes is going to be dependent on these sets of weights, right? So gradient descent is based on the idea that error is a function of the weights. And our goal is to reduce that error. So gradient descent tries to move the network towards error minimum. And computing the gradient means getting the direction towards this error minimum. And then when we adjust the weights, we are using that computed gradient to move the weights in the direction of lower error. And when we talk about backpropagation, it's basically using the gradient descent to first adjust the weights of the last layer, and then propagating the error back to each of the previous layers to adjust their weights. So graphically, we can look at gradient descent as, this plot is showing error as a function of weights, right? And here we see that, let's say this is our current weight at, let's say 0.5. Then basically gradient descent is going to give us a gradient, which is basically both the direction as well as the absolute value of the gradient. And so it tells us to move in this particular direction because we know in this function, this is the optimal value, right? So once we have this gradient, we can update the weight by subtracting this gradient. And we're subtracting because it's pointing in this direction, right? So the direction is telling us whether to subtract or add. And that will move us towards this optimal value of minus 0.5 in this case. And this looks parabolic because here we've assumed that the error function is squared error, right? But this can take different shapes depending on what loss function we are using at the output layer. And so if we look at multiple dimensions, so this was just one dimensional, right? So this is just one weight vector, but we usually have multiple weight vectors. And so here, this is showing in 2 dimensions, an analogous picture where you have one weight, gradient of first weight component, and then the gradient of second weight component. And what you do then in gradient descent is you move in the direction of the combined gradient, right, in the resultant direction. And that takes you towards optimum. So next I'm going to talk about how we are updating the weights. So I'm going to start with the final layer update. And so basically we start if we look at this network and we think of this network, we look at the last layer, and we know that the activation of the last layer is given by this equation, where Wk is the set of weights on these connections, and Hk is the activation vector at the previous layer. And here I choose my activation function to be a sigmoid. And so in this case, I also choose my loss function or error function to be, again, squared loss. And so now in order to compute the gradient of this error with respect to the weights, we can write the gradient as this. So basically, the derivative of error with respect to the weight vector Wk is given by the derivative of error with respect to y times the derivative of y with respect to s, where s is this, right? And then times the derivative of s with respect to Wk. So this is basically using the chain rule, right? What we want is the derivative of error with respect to weights, because we want to update the weights. And the way we compute it is by using the chain rule. And so in this case, what we see is that first we compute the first term, right? The derivative of error with respect to y. And that can be computed using this equation. And so here we know that the derivative of error with respect to y can be computed using this equation. And this is how we compute it, right? So this is a simple derivative where this is going to be -2 times t minus y, and the 2 and 2 get cancelled with each other, and we get this. So next we compute the derivative of y with respect to s, this term highlighted in green. And so y we know is a sigmoid function, and you don't need to know the details, but it's the derivative of a sigmoid is just sigmoid times 1 minus sigmoid. And since sigmoid is just equal to y, we can simplify and write it as y into y times 1 minus 1. And then we come to the last term, which is derivative of s with respect to weights. And that can be computed from this equation here, right? So now we know that the derivative of s with respect to weights is just hk, because this term will give us hk only when, this k, when we have h of a particular h corresponding to particular weight vector k, right? And it'll be 0 at other times. So we get this term hk here. And so if we combine these three terms, we get this, this combined derivative. And so basically, this can be used to, this is a gradient, basically. This is a gradient terms which can be used to update the weights wk in the last layer. And so another thing which I should mention is that usually we also add this term called learning rate, which will determine how quickly or how slowly we'll update these weights. So this is basically the change in weights is going to be your weight gradient times your learning rate. And then basically in this case, I was showing a network which had only one output. If we have multiple outputs, then our error just becomes sum of the errors at each of the output nodes. And the weights can be adjusted based on which node they are pointing to, right? So the change in weight, connection strength from node K to node J is dependent on the terms associated with these two nodes, right? The terms associated with node J and node K only. And basically, we can also then look at, okay, do people have questions so far? Oh, I skipped the hidden layer. So I should also mention, so till now we looked at updating the weights of the last layer, but next question is how do we update the hidden layer weights? And I won't go into the theoretical details of it, but I want to point out that we usually compute this weight, this term delta, which is basically the gradient. It's another way of writing the gradient. And we know that in our last layer, it was given by t minus y times y prime, right? So t minus y was just, if we go back, t minus y was this term, derivative of error with respect to y, and this whole term can be seen as y prime or derivative of y. And so this is how we write a gradient and for the last layer. And if we look at the gradients for the hidden layers, it turns out that we can show mathematically that it can be written in this way, where Wji are connections from weight connections from nodes I to nodes j. And so this brings us to the universal update formula for gradient descent. So basically, given the weight between any node k and node j, the change in weight is given by the learning rate times this term delta j times h of k, right? Where h of k is the activation of node k, and delta j is the gradient corresponding to node j here. And so this is basically also sometimes called the delta rule, and this is kind of the main learning rule for backpropagation. And this is not perfect. So we've established that we can use gradient descent, and we can combine that with backpropagation to update the weights of all the layers in the network. But it has its own problems. So one problem is that if you have the learning rate too high, then your error, basically your weight computations would be jumping very erratically, and it would be very difficult to actually reach this minima. Because even when you are close to the minima, you will be jumping very erratically around it, and you wouldn't be able to reach this minima. And similarly, sometimes your loss landscape can look like this, where you have local optimums and global optimums, and you can get stuck in the local optimums. And so that can be very difficult. And so in fact, even the deep networks which we use today, there's no guarantee that they actually converge to a global optimum. Sometimes they actually do get stuck in local optimums, but nevertheless, they still perform very well, maybe because the local optimum is kind of very close to global optimums in those cases. And then there's another problem where if you're using a very low learning rate, then your convergence rate, and you're very far from your optimum value, then if you had a very bad initializations for the weights, it can take you a long time to converge. Right. So one of the solutions to this is to use an adaptive learning rate, where you can change your learning. You can have a bigger learning rate in the beginning, so that you can come near to the optimum. And when you reach near the optimum, you can reduce your learning rate so that you have a higher chance of reaching the optimum. And there are different optimizers, which we'll see are implemented in TensorFlow, which will show us, which basically implement this adaptive kind of learning rate. One of them is called Adagrad. And this takes us to stochastic gradient descent. So stochastic gradient descent, basically so far we've seen that you train on the entire data set, and then you compute one weight update. And then you again train on the entire data set, and then you again compute one weight update, and so on. What stochastic gradient descent allows us to do is it proposes that most of the times data sets have redundancy in them. And because of that, instead of computing the full gradient on the full data set, what we can do is we can divide the data set into batches, and we can compute weight updates after a certain batch, after the model has been trained on a certain batch. And so the extreme version of this is online stochastic gradient descent, in which you train the model on one particular training example and you update the weight. And then you train the model on the second and you update the weight. So if you update the weight for every single training example, then it's called online stochastic gradient descent. And another version is mini batch stochastic gradient descent, where instead of updating for every single sample, you just form small batches of training samples. So that's kind of a middle ground between updating on every sample versus updating on the entire data set. So now you have small batches, and you can update your weights after training on some subsets of your training set. So that's stochastic gradient descent. And the last thing I want to point out is a lot of these models will have this problem of overfitting, which means that when they're trained on a training set, they'll perform very well. But when you test them on a test set, then their accuracy will go down relative to their performance on the training sets. And so the solution to this is regularization, which means that basically any technique that reduces overfitting in a network can be termed regularization. And there are multiple ways of regularization, and we'll cover some of them next time. But one of the ways is dropout. So in dropout, what we do is we just randomly remove some hidden units in the network during training. So for instance, this is a fully connected network, but what we would do is during training would randomly just turn off these units, right? And if these units are off, then the connection weights from these units connecting to and from these units become irrelevant. And so what this allows us to do is it reduces the reliance of the network on just some specific weights, and hence reduces overfitting. So yeah, so that's all I have, at least for the slides part. Do people have questions at this point?